This section is just a quick review of inverse functions. You might recall from algebra that we can use the horizontal line test to determine if a function has an inverse, and basically what that does is that shows whether the function is one-to-one. So basically this function here passes the horizontal line test, so it's one-to-one. This function fails the horizontal line test, so it's not one-to-one. And these two functions also fail the horizontal line test and are not one-to-one. You can actually examine functions and try to determine if they're one-to-one. So for instance, like a linear function like f of x equals 3x minus 2, if x is negative 2, y will equal negative 8, but if y is negative 8, if you solve for x, you'll only get one value for x. So basically a function is one-to-one if each y value leads to only one x value. If y is negative 2, it leads to 1, and it leads to 0, and if y is 1, it leads to x equal 1. But these other two cases, you can clearly find a y value that corresponds to two different x values. Here, if y is 0, that's actually going to be the same as corresponding to x equals negative 2. That should actually be minus 4 there. But anyway, if y is 0, then negative 2 squared minus 4 is 0. But also 2 squared minus 4 is 0. So here you have actually two different x values that correspond to this y value. So therefore that function is not one-to-one. For this function, you can see that if y is 5, if you plug 2 in here and check it, you'll see that you get 5 for the y value. But also if you plug 6 in, you'll get 5 for the y value. So you see that 5 corresponds to 2 and 5 corresponds to 6. So that definitely is a y value that corresponds to two different x values, so therefore that one is not one-to-one. Well, two one-to-one functions, f of x and g of x, are said to be inverses of one another if their composite functions equal x. So basically the composition just returns the value x. So here's two functions. Now I know these functions are inverses, and let me show you how I know this. If you compose f with g of x, that means you take the f function 4x plus 11 and replace it with this g function here, and then simplify it, you're going to get x. Or if you do the other way, say you take the g function 1/4 x minus 11/4 and you replace x with the f function 4x plus 11, and then you simplify that, you're going to get x. So that basically proves that those two one-to-one functions are inverses of one another. Now if you were to graph these two functions, you would see that they're reflections about the line y equal x, which is always true about functions that are inverses of one another. They're reflections about the line y equal x, and that's this dotted line right here. Here's another example, and I'll let you can pause the video if you want to, but show that f of g of x equals x and that g of f of x equals x for this function f of x here and this function g of x here. And once you've shown that, then you basically prove that they're inverses. And also look at the graphs of the two functions. Notice that the two graphs are actually reflections about the line y equal x. Now the steps to finding the inverse of a one-to-one function are basically this. Write the function as y equals f of x, then switch the x and y values, then solve the function for y, and you'll get a new function, and that new function is actually the inverse. So let me do the second one here because it's a little more difficult. The first one's pretty easy, but let me do the second one and then you can do the first one. Okay, so here I have f of x equals x minus 1 over 3 minus x. So let's write that as y equals x minus 1 over 3 minus x. So that's step 1. Step 2, let's replace y with x, and everywhere there's an x, let's replace it with y. So we'll put a y here and a y here. Well, now what I want to do is I want to solve this equation for y. So here's the equation that I started with. Well, what I want to do first is eliminate this denominator, so I'm going to multiply both sides by 3 minus y. Well, if I multiply x by 3 minus y, I'm going to get 3x minus xy. And if I multiply this fraction by 3 minus y, I'm just going to get y minus 1. Okay, well now what I can do is I can put the two y terms on the same side. So I can get this minus xy and this y on the same side. So if I move the minus xy to the right, that becomes plus xy. And then I'm going to move the minus 1 to the left. So therefore, I get 3x plus 1 equals y plus xy. Let's turn that around and say it this way. Y plus xy equals 3x plus 1. Now I can factor the y out, and I get y times 1 plus x equals 3x plus 1. So now if I want to solve for y, I get y equals 3x plus 1 over 1 plus x. And that's going to be the inverse of the original function. So the inverse of f is actually 3x plus 1 over 1 plus x. The domain and range of an inverse and its function actually just swap places. So for instance, if f of x has domain 0 to infinity and range from 2 to 5, then the inverse will have domain from 2 to 5 and range from 0 to infinity. So if you take this function that I dealt with a minute ago, x minus 1 over 3 minus x, well, this function has domain x cannot equal 3, so the domain would be negative infinity to 3 union 3 to infinity. Well, then that means for the range of the inverse, so this function, y cannot equal 3. So therefore, for the inverse, the y value will not be able to be 3. So the range for the inverse will be the same as the domain for the original function, negative infinity to 3, 3 to infinity. And then if you look at this function, it's easy to determine on this function, the inverse, that x cannot be negative 1. So the domain would be, for the inverse, would be negative infinity to negative 1, union negative 1 to infinity. So that means that the range for the original function would be the same thing. Y cannot be negative 1. Go ahead and read this little blurb here. It just talks about the continuity and differentiability of inverse functions. And so there's 4 things here. If a function is continuous on its domain, then its inverse is continuous on its domain. If a function is increasing on its domain, the inverse is increasing on its domain. Or if a function is decreasing on its domain, the inverse is decreasing on its domain. And if f is differentiable on an interval containing c, as long as f prime of c does not equal 0, then f inverse is differentiable at f of c. So these are the 2 functions that we found were inverses a few minutes ago. And notice that both of these functions are increasing throughout their domain, and they both are differentiable at all values except negative 3, because f prime of negative 3 is 0 for the one function, but g prime of negative 3 is not defined because you get a vertical tangent line at negative 3. And so there's the negative 3. So that's where you get like a vertical tangent line right there. Okay, now this function is actually going to be used a little bit later. I should say this theorem is going to be actually used a little bit later. But basically it says let f be a function that's differentiable on an interval I. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not 0. So, moreover, the derivative of g is 1 over the derivative of f evaluated at g of x, as long as that derivative evaluated at g is not 0. Okay, so let's put this in perspective. Now, we know these 2 functions are inverses of one another, correct? Okay, well, the derivative of f is 3x squared. The derivative of g can be found to be 1 over 3 times x plus 3 to the 2/3 power. Now, let's go ahead and find f prime evaluated at g of x. Well, here's f prime, and if you plug g of x in there, then you're basically going to get 3 times this function squared. So you get 3 times x plus 3 to the 2/3. Well, the theorem says that the derivative of g is 1 over this value here. Well, we already know the derivative of g is this, which is actually 1 over this value here. So it actually does prove the point of the theorem. Suppose I want to find the derivative of the inverse of this function at 2. So in other words, I want to find the derivative of f inverse at 2. Now, what we could do is, first of all, find the derivative of this function, which is 2 over x minus 3 quantity squared. And then we can easily show that f prime, if we evaluate f prime at 2, we're actually going to get 2. And so now we want to find the derivative of the inverse at 2. Well, from the theorem, it says the derivative of the inverse at 2 is 1 over the derivative of the function evaluated at what you get when you evaluate the inverse at 2. So finding f inverse of 2 is easy enough, since I know the inverse is this function. So f inverse of 2 would simply be 3 times 2 plus 1 over 1 plus 2, which is 7/3. Now, to finish up, the f inverse of the derivative of f inverse at 2 is 1 over the derivative of f inverse at 2, which is 1 over the derivative evaluated at 7/3. And now, if you evaluate the derivative at 7/3, remember this was the derivative, so if you evaluate this derivative at 7/3, you're going to get 2 over 7/3 minus 3 quantity squared, which is 2 over negative 2/3 quantity squared. So it's going to be 2 over 4/9. So that's going to be 1 over 18/4, which is 4/18 or 2/9. So I claim that the derivative of the inverse at 2 is 2/9. Now, if you don't believe that, then find the inverse and then take its derivative. So if you found the derivative of this, you would actually find that it's 2 over x plus 1 squared, and then if you evaluate the derivative, that derivative at 2, you're actually going to get the same thing I got up here, 2/9. Well, this actually is used later, or can be used later in finding the derivative of the exponential functions by knowing that they're inverses of log functions. Okay, the next sections we're going to talk about the exponential function as an inverse of log functions, and then we'll move on from there and talk about the inverse of trig functions.